Welcome to the video lesson for section 8.6, Counting Principles. We're going to look through how many different ways you can arrange a collection of objects to see the different amount of combinations you can come up with. Let's get started. The fundamental counting principle states that if one event can happen m different ways, and a second event can occur n different ways, then our combination of the two events can occur in m times n different ways. So we take the number of outcomes for our first event and the number of outcomes for our second event, and we multiply them together. Let's go ahead and look at an example of this. We're going to flip a coin, and we're going to flip the coin 2 times. The first time that we flip the coin, we have two outcomes. We're either going to have heads or tails. So again, the first flip had two different ways to flip the coin. With our second flip, we're again going to have two outcomes. So if we ended up getting a heads for our first flip, again, we see we have heads or tails with our second flip. If instead we had tails for our first flip, again, we would have heads or tails for our second flip. So once again, we have two outcomes. So the first flip had two ways. The second flip had two ways. If you multiply those together, we get four ways, which are the actual outcomes. We could get heads and heads, heads or tails, tails or heads, and then tails or tails, because in this case, the order definitely matters, the first flip versus the second flip. And we see that we have our actual outcomes here listed in our sample space: heads, 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 tails, tails, heads, or tails, tails. For our next example, we have a meal that consists of a main dish, a side dish, and a dessert. For our main dish, there are going to be four different ways we can get our main dish. We have two different side dishes, and then we have five desserts. So the question is, how many different meals can we make if those are our options? Going off of our formula of m times n, in this case there are three things, so we have essentially an m, an n, and a q. We're going to multiply all of our options together. So we can see that there are four different main dishes. We're going to take that value and multiply it by the number of side dishes, so times two side dishes. And then we multiply that by the five desserts that we have available, and we get a total number of 40, which means that we have 40 different meals available. Here we're going to determine how many pairs of letters can be made from the English alphabet. And one thing that's going to be very important as we do these things is if something can repeat or not. In this case, our letters can definitely repeat. So for our first letter in the alphabet, there are 26 different letters to choose from. So we have 26 for our first event. And then picking our second letter, we again want to think about how many there are in the alphabet. Again, there are 26. So we have 26 times 26, get a total of 676 different combinations of two letters. As we are ordering or arranging all of our different combinations, we have two separate types of events to think about. One of them are permutations. So a permutation consists of n elements, of which we take r at a time. Sometimes it could be all of them, sometimes it could be a subset. The important thing for permutations, though, is that the order matters. So this would be an example of you have 20 people running a race. How many different ways can you choose the top three finishers? We can definitely say order matters because getting first place versus second place versus third place is a big difference. We could have a committee of people, and from that committee of people, we're going to select some offices. So maybe the president, the vice president, and the treasurer. Again, because we are ranking the pick or giving a specific office to a pick, the order definitely matters. So for examples that are permutations, the order you're picking something definitely matters, so it affects how we calculate it. Building off of our definition of permutations, we can see here that permutation is an ordered arrangement of n different elements. That word arrangement is a very key word that tells you we're doing a permutation as opposed to a combination that we'll discuss later, and it tells you the order is going to matter. So our question then is, how many permutations are possible if you have three different colors, red, white, and black? Because it's a permutation and we know the order matters, we can't repeat colors. So I can't have any option where all three colors are the same. So to finish answering this question, we have three choices for our first color, any of the three colors, two choices for the second because we can't repeat one we've already used, and then only one choice for our third. Because there's only three colors, we could build all the options, and we can see all the different arrangements here. So we have red, white, black as one arrangement, then we have white, black, red as a second arrangement. And if you look at all the different arrangements here, there are 6 total arrangements. When we only have a finite number of elements, it's kind of easy to build your different arrangements. But if we had a large amount of colors, it might be a little more challenging. So there's an algebraic approach as well. Going back to what we stated here, because there's 3 choices for your first, 2 choices for your second, and only 1 choice for your third color, we can go ahead and multiply those values together. So we have 3 times 2 times 1, which is also known as a factorial, where you're multiplying all the numbers from n to 1 together, and we see that we get our correct answer of 6 again. All right, for our permutation question here, we want to know how many different possible arrangements are there for all the letters that spell out the word or the phrase, math is fun. I could take all of my letters and rearrange them if I wanted to. So I could start by switching out my A and my M. So I could have A, M, and then the same exact letters as followed. Or maybe I could switch the N and the U at the very end. I could even rearrange these words. So I could say maybe, is math fun? The problem here, because we have so many letters, building all the different arrangements would take a very long time. So we're going to approach this with an algebraic process instead to kind of speed it up. Looking at our phrase, math is fun, the first question we want to ask is how many letters are there? So if we count them all up individually, then we have a total of 9 letters. Since we're going to be using all of these letters in a permutation, we have 9 choices for your first letter, 8 choices for your second letter, 7 for your third, and so on until we get all the way down to 1, which is a factorial. So we can go ahead and say that it is 9 factorial, which simplifies to be 362,880. So there's that many different arrangements of letters in the phrase math is fun. With the previous 2 examples, we were taking all of our elements and arranging all of them. So for our permutation, we had simply n factorial. We don't always use all of the elements though. So here we can see that we have a permutation of n elements where we're taking r at a time, which means we're not using all of the things within our example. Again, we know that order is important, so this is definitely going to be a permutation. The question is, how do we manage this type of question? So for an example, we have 5 projects that are entered into a science contest. How many ways can the projects come in first, second, and third? Since we are ranking our projects first, second, and third, we know that order is important, so we can verify this as a permutation. We're going to go ahead and go through the different ways we can give out first, second, and third now. Because there are 5 different projects, for your first place prize, we have 5 to choose from. And you can't take that same project and give it second place, so now there's only 4 for your second place prize, and then 3 for your third place prize. By multiplying all of those together, we get our answer of 5 times 4 times 3, or 60 total ways to give out first, second, and third if you had 5 different projects. Again, our example of only having 5 projects is a finite amount, so we want to make sure that we can expand this to any amount of objects that we start with and any amount of objects that we are actually arranging. So we have a formula. The formula for permutations of n total objects, where you're taking r at a time, is the following. We have NPR is equal to n factorial over n minus r factorial. Within this formula, n is going to represent the total number of things in your collection, or the total number of things that we're looking at, whereas r is going to be the amount of things that you're taking or the amount of things you're arranging. If we apply this formula to the last example of 5 science projects where we're giving out first, second, and third, we can say that there were in fact 5 total projects. We're going to be arranging 3 at a time because we're giving out first, second, and third place. So if I plug those values into my formula, I see that I have 5 factorial over 5 minus 3, which is simplified to be 2 factorial. Expanding out my factorials, again, they are n all the way down to 1 being multiplied together. So 5 factorial will be 5 times 4 times 3 times 2 times 1. And then we see that 2 factorial is just 2 times 1. We can go ahead and cross cancel some of this, so I can cancel out the 2's and the 1's, and we get the same expression we had for our last example, where it's 5 times 4 times 3. So sometimes we can just rationally think about what the values are going to be. Sometimes it's so large that having a formula is definitely going to be nice. But here we see a different way to go ahead and get the same answer. For our next example, we want to know how many ways are there to determine first, second, and third place winners if there are in fact 8 contestants. So for our formula, again, n is going to be the total number of contestants here, whereas r is going to be the amount of places we're giving out. In this case, we're giving out the top 3. So when I go ahead and plug this in, we see that we have 8p3 is equal to 8 factorial over 8 minus 3 factorial. We can go ahead and simplify this 8 minus 3 to be 5 factorial. So we have 8 factorial over 5 factorial. If we were to expand this out, we would get the 5, 4, 3, 2, and 1 in our numerator to cancel with our denominator. So we can simplify it to simply be 8 times 7 times 6, which means there are 336 different ways to pick 3 winners out of 8 contestants. For distinguishable permutations, these are situations where you have elements that are the same within our collection or maybe repeat. So for example, to highlight this, The question is, how many distinguishable ways can the letters in stats be written? And the reason why we need to distinguish things is I have an S and I have another S. So if I simply were to switch those two, you wouldn't be able to tell because the objects are identical. Or if I were to try and switch the T's, again, because the T's are identical, if I switch their positioning, you couldn't tell. So we have a smaller amount of different arrangements because we can't tell the difference between elements are in fact the same. So our formula for the number of distinguishable permutations of n objects is going to be n factorial divided by n1 factorial times n2 factorial times n3 factorial all the way to nk, where all of your denominator values add up to be the total number of elements you have. So n1 plus n2 plus n3 is going to equal n. If we take this and apply it to our example of stats, we can see that there are in fact 5 different letters, so our n value is going to be 5. The S repeats twice. We have 2 different S's, so we have a 2 factorial. The T also repeats twice, so we have a 2 factorial for that. And the A value repeats once. If we take these 3 values and add them together, we end up getting our N, which is kind of what we're trying to show here. And when I simplify this, I get 120 over 40, which simplifies to be 30 different distinguishable permutations for the word stats. For our next example of distinguishable permutations, we have a question. How many distinguishable permutations are there for the word parabola? So what we're looking for here is things that actually repeat. And I noticed right away that the A repeats 3 different times. No other letter actually repeats. So when I go ahead to answer my question, I know that I have 8 objects and I have 3 A's that are repeating. When we go ahead and plug everything into our formula, I have 8 factorial over 3 factorial. I want to point out here that for my denominator, I don't have all the other factorials because I've already simplified things. The other 5 letters, the P, the R, the B, the O, and the L, they all have a 1 factorial, which is just 1. So when I multiply all those together, it's the same as having just a 3 factorial. So kind of a shortcut here is when you're dividing, you really only need to divide by the things that repeat because the things that don't repeat have, again, a factorial of 1, which is not going to affect your outcome. When I go ahead and plug this into the calculator and I simplify my answer, I do, though, get 6,720 distinguishable permutations for the word parabola. For our next example, the question is how many distinguishable permutations are there for the word, or actually the name, Chuck Norris? First thing we want to consider is how many total elements are there, so how many total letters are there? In this case, there are 11. The next thing we need to look at is what is repeating. So I can see that my C repeats, and it repeats twice. I can also see that the R repeats twice. So I want to make sure I consider that there are 2 C's and 2 R's. When I go to plug this in, my N value is going to be 11, and then I have my repeating values, which are going to be 1. All the other letters that don't repeat have a value of 1. And remember, I kind of omitted those because it's like dividing by 1, which is not going to affect our outcome. So you can see that in my formula, I have our N factorial divided by the repeating letters, 2 factorial and 2 factorial. Again, I omitted the 1s because it's not going to affect our outcome. But when I plug this into the calculator, we do get our final answer. For our next type of problem, we have combinations. For combinations, the order doesn't matter. And as a result, you see that our formula is a little different. It has this extra r factorial on the bottom. Dividing by the extra r factorial is going to reduce the number of combinations. Since order doesn't matter, we're not going to have the same amount as you did if you had permutations. To further clarify this, I just want to elaborate. So n, again, is going to be the total number of things in the collection. R is going to be the number of things that we are taking for our combination. And we can see how that's going to factor into our formula. So we have an example here. If we had 4 choose 2, that would mean that we have 4 objects. We're choosing 2 of them at a time. We would have 4 factorial in your numerator divided by 2 factorial times 2 factorial. If you wanted to expand and simplify this, we would get 4 times 3 times 2 times 1 as our definition of factorial there. And then we have 2 times 1 times 2 times 1 for your denominator. We could quickly cross cancel some things, which means we have 4 times 3 divided by 2, and we get a final answer of 6. For our next example, we want to know how many different poker hands are possible. So we have to kind of determine here, does order matter or not? Does the first card I get versus the second card I get affect what my hand is going to be? And the answer here is no, because all 5 cards create your hand, so the order you're receiving the cards in doesn't matter. So definitely this is a combination. For a deck, there are exactly 52 cards. So we know that our end value is going to be 52. Your poker hand has 5 cards in it, so we have 52 objects. We're going to be choosing 5. Now notice this word choosing 5 is different than what we use for our factorial. It was arranging or picking. So the language in each question is going to directly affect or influence what we're going to be using, or maybe hint at the correct formula. So again, for a permutation, you're picking or arranging. For a combination, you are choosing. When we go ahead and plug this into our formula, we have 52 choose 5, which is then going to be 52 factorial over 52 minus 5 factorial times 5 factorial, which will simplify to be 52 factorial over 47 factorial times 5 factorial. And for this one, I would definitely plug it into a calculator. I think expanding it and simplifying it would be a little tedious. But if you do it correctly, you do get the correct answer of 2,598,960 different poker hands. All right, in this example, the question is, how many ways can you choose 7 people from a committee of 21? Again, we have this word here. We have choose. That's going to help us identify that it's a combination. Also, if we're taking 7 people from a committee of 21, does the first person selected have any difference in the second person selected? And again, the answer is no, because they're all going to be in the same committee and have the same role. So when we're answering our question here, we're going to be using our combination formula. Our end value is going to be 21 because there's 21 total objects. We're going to be choosing 7 at a time. So we know, again, it's going to be a combination. When we plug that into our formula, we get 21 factorial over 21 minus 7 factorial times 7 factorial. And then we can go ahead and simplify that. And once again, this is kind of large to do by hand. So I would plug that into the calculator and simplify it to get 116,280 different combinations. And for our final example, the question is, how many different ways are there to choose 6 out of 10 books if order does not matter? So there's 2 different hints here. We said choose 6, and also we are told order doesn't matter. So I know it has to be a combination. I'm going to go ahead and plug it into my formula. I know that my N value is going to be 10 because that's the total number of books. My R value is going to be 6 because that's how many I'm choosing. So my formula is going to end up being 10 choose 6. And then when I plug that in and simplify, we get 10 factorial over 4 factorial times 6 factorial. One kind of trick we can see here, specifically with the combinations and the permutations, is I can expand my numerator until I get to the larger value of my denominator. So notice that I stopped at 6 factorial because I'm also going to have a 6 factorial in my denominator. I can directly cancel those. We can do some other simplifying here too if we're asked to do this by hand, or we can plug it into our calculator and we get 210. Which means that we have 210 different ways we can choose the 6 books if there are 10 to choose from. All right, that does it for our notes. Go ahead and get started with the homework, and good luck.